Through Heritage Lottery funding, Capturing Our Coast presents Race 2 Recovery. The results. Ready? 3, 2, 1, go! During this short feedback video, we will show you the exciting results from our Race to Recovery survey and the outcome of all your hard work over the past 2 years. But before we get stuck in, let's have a look at the science behind the study and what we were hoping the data could tell us. Firstly, let's talk about resilience. In this video, when we refer to resilience, we are talking about ecological resilience, meaning how well a group or community of seaweeds and animals cope with a particular disturbance, and if they are completely removed by this disturbance, how quickly they come back and make a full recovery. Resilience is very important to understand, especially in the midst of a changing climate, where disturbances such as storms may become more frequent and/or more severe. We need to understand how communities are affected in order to predict the wider impact and work out which species are the most vulnerable and need more conservation effort. Why does biodiversity matter to resilience? Biodiversity is the variety of species living in a community. High biodiversity is linked with high resilience. High levels are important for communities to keep functioning when hit by a disturbance. The more species you have, the higher the biodiversity. The higher the biodiversity, the more stable the community is, and the higher resilience it has. The Amazon rainforest is a good example of a highly biodiverse community. In fact, it is thought that up to half the world's plant and animal species live there. Recent studies show that the Amazon may be building resilience to climate change due to its high plant diversity. Each species has a job to do, so the more species you have, the more likely it is that multiple species will do the same job. This is called functional redundancy, meaning that if one species is removed, another one can take over. There are lots of examples in the intertidal zone where different animals and seaweeds have similar roles. Canopy seaweeds provide shelter from the sun for crabs, anemones and many other species. If, say, bladderwrack was to disappear, then egg-wrack could provide the same amount of shelter for those who need it. Grazing animals such as limpets and snails keep the seaweeds from overgrowing and hogging up all the space and light. If one was taken away, the other could carry on the grazing job. Aside from helping to keep the community functioning, the more species you have, the more likely it is that some of these species will be more tolerant to a particular type of disturbance. This means that at least some of the species within the community may survive or have a quicker recovery time. So far, we've referred to disturbance as a negative thing, but this isn't always the case. How it affects the community depends on many factors, including how severe and how frequent the disturbance is, and how resilient your animals and seaweeds are. Communities living in areas that have a moderate amount of disturbance tend to be the most biodiverse and resilient. This is because if you have too much disturbance going on in an area, for example, on a pebble beach with lots of strong wave action, the environment becomes too difficult to settle on or live in. Seaweeds and animals find it too hard to colonize with pebbles moving around and scouring each other, scraping off any signs of life. On the other hand, if you have too little disturbance, a tougher, stronger species such as egg-wrack will outcompete and dominate an area, restricting other species' access to space and light. Disturbances can range from a co-coast volunteer placing a quadrat down on the shore and moving the seaweed canopy, to those that have a far further reach, such as an oil spill. A pressing issue causing many different disturbances that we are all aware of is climate change. Climate change is becoming more concerning and could have a great effect on marine life. In the intertidal zone, wave action is strongly influenced by the weather, especially bad weather. Powerful winds generate powerful waves, which can dislodge animals and seaweeds and destroy habitats, leaving nothing left but a bare patch of rock. It is thought that as global average temperatures rise by more than 3 degrees, the intensity and frequency of the most extreme winter UK windstorms will increase. So, the big question is, how will this affect marine life, especially the species most vulnerable to changing exposures, such as animals and seaweeds living in intertidal zones on the rocky shore? If they are removed from the shore, will they return? Rocky shores are important sources of food for not only animals within marine food webs, but terrestrial species too. They're also a great place to study the effects of different stresses on ecosystems because they are visible and accessible, which helps us to survey them. Their inhabitants provide us with the major components of different medicines, such as antibiotics and anti-inflammatories, and they are great places to get outdoors for mental well-being. And we haven't even mentioned their great economic value with industries such as mussel and oyster farms. Because of their high importance, we need to find out how they will react to the impacts of climate change and put in place management plans to protect them for future generations. And so, cue Race to Recovery. Over to you, Hannah.
Over the past 2 years, Capturing Our Coast has run a survey called Race to Recovery. This survey was designed so that volunteers from different regions could collect data from areas where storm damage had been simulated and look at how a variety of species reacted. With the data gathered, we were able to get an insight into how biological communities may recover from this type of disturbance. For example, which species appeared first and how long it took communities to re-establish fully. From spring 2016, 14 rocky shores were monitored around the UK, from 5 Capturing Our Coast hubs in 4 different areas. Small patches of each shore were cleared of seaweed and animals, and 63 volunteers assisted Co-Coast staff to survey these patches every 3 months over a 2-year period. During this time, data was collected from 1,817 quadrats, which equates to an area similar to 2 full-size tennis courts. Within the surveyed patches, volunteers recorded the abundance and lengths of large canopy seaweeds, small turf seaweeds, and green ephemeral seaweeds to determine any variation within communities between disturbed and undisturbed areas. Here are some of the things we found. Although there was a lot of variation between regions, as well as between different shores within these regions, a similar trend in succession was found over all the sites. Succession is the order in which species appear and disappear at different stages of recovery. We found that the green opportunistic seaweed returned first. Then, as the brown seaweed began to settle and take hold, the green seaweed declined. As all the seaweeds returned, the limpets returned to graze on the biofilms and juvenile seaweeds. Interestingly, we found it took almost 1 year for the abundance of brown seaweed from disturbed areas to match that of undisturbed areas, and it took 2 full years to reach its original length. This could have great implications for other rocky shore species. Earlier in the video, we explained that brown canopy seaweeds create important shelters that can protect other organisms from predation, extreme temperatures, and drying out. Without them, other organisms may not be able to inhabit the same areas, therefore restricting their distribution and reducing the biodiversity of the community, which could impact its resilience. So these patterns were seen in all our sites, but did anything differ between regions? Let's have a look. Overall, the North Wales data showed a textbook example of succession and how the recovery of our key species, the green seaweed, the brown seaweed, and the limpets. It also highlighted the variation between shores within a region. For example, Porthrewin had a slower rate of recovery than Triada Bay. This could have been due to a variety of reasons. For example, Triada Bay is subject to more wave action and so may be more resilient to associated damage. However, the rocks at Porthrewin have much smoother surfaces and there are fewer cracks to offer protection for juvenile seaweed to grow and develop. Either, or a combination of these reasons, could be causing our results, and so further investigations are necessary. In northeast England, there was an interesting sharp spike in green seaweed cover in the disturbed areas after 15 months. Could this be a result of what is called the ephemeral bloom, that is seen around springtime and is caused by fast-growing and short-lived ephemeral seaweed such as the greens, taking advantage of increased light and warmer conditions that promote their growth? Or could it be regrowth following Storm Doris that hit the UK at the end of February 2017, just prior to our green seaweed spike? Whatever may have caused this spike, it isn't seen in the undisturbed plots, which could be attributed to the well-established brown seaweed stopping the greens from getting a look in. The data from southeast England also showed a spike in green seaweed in the disturbed areas after 15 months, although it was far less pronounced than in the northeast. In the southeast, the relationship between limpet grazing and total seaweed cover in the undisturbed areas is also very clear. Generally, when there is a decline in limpet abundance, there is an increase in total seaweed cover, and when there is an increase in limpet abundance, there is a decrease in total seaweed cover. And finally, to Scotland. Overall, Scotland was the fastest region to recover, with total seaweed cover in disturbed plots reaching the same level as the undisturbed plots after only 6 months, and the percentage of brown seaweed cover in under 9 months. Could this be a result of the harsher conditions felt up north, resulting in a faster recovery time? As we discussed earlier, when a species encounters a disturbance repeatedly, it may become more resilient to this disturbance. If the wind is stronger in this region, it could mean stronger wave action, and therefore the species living there are more resilient to stormy conditions. All of these variations generate useful questions that we can work towards answering in the future to form a more complete picture of how communities may recover after increased or more frequent storm damage. The Race to Recovery data produced some interesting results and identified a clear pattern of succession across all regions. In addition, the 2 years that it took brown seaweed from disturbed areas to grow in length to match the brown seaweed from undisturbed areas shows us that it can take a considerable time for conditions to re-establish and normal function to ensue, even when it may appear that a community has recovered. Lastly, the variation of recovery speed within and between regions has highlighted some intriguing possible mechanisms, such as shore exposure and rock surface type, which make a great next step for further investigation. And finally, and most importantly, just before we go, we would like to thank all the volunteers that have taken part in the Capturing Our Coast project around the UK and contributed data by surveying one of our species packages, helping search for those sneaky invasive species or cute beach babies, or should we say mostly gelatinous beach babies. Please get in touch and let us know which were your favourite parts of the project and which bits we could do better. But bear in mind, we haven't yet gained the power to change the weather or prolong the summer.